right, so we're going to get started here on Module B. I am recording this for those who are not here today. All right. Does that look like it's in focus to y'all?
Yeah.
Okay, good.
So what page are you?
19. Right, so here we go. We're going to review water. So this module is still about water. So one of the things I want you to remember, a couple of things I want you to remember, and this would be for, remember next week we're going to be having a quiz over this stuff. All right? So, first of all, H2O is the chemical formula for water. Y'all already know that, right? H2O is the chemical formula. Water is polar. Do you remember what that means?
It sticks to itself.
It sticks to itself. Good. Anything else? What does polar mean?
It dissolves.
It's a universal solvent. We have that for our next one right here. So it dissolves a lot of things. Does it dissolve everything? No. Remember, oil didn't dissolve in it, right? But also remember, polar means that it has a partial positive charge and a partial negative charge. It's got charges associated with it. All right. So those are three important things to remember for next week's quiz. Intent. And then the fact that water sticks to itself. That's what Zoe was saying right now about water sticking to itself. It's bonding to itself. So it keeps water a liquid at room temperature. This is why it's so important. Okay, and so what's happening there is that partial negative charge on the oxygen is attracted to the partial positive charge on the hydrogen like a magnet. So they're kind of sticking together there. If they did not attract, the gases would be not forming a liquid at normal temps. All right, so therefore it'd be forming a gas too easily. If it wasn't sticking to itself, I told you it's sticky. If it weren't doing that, it would be evaporating very quickly. And if that were the case, we wouldn't have liquid water on the earth. And if that were the case, we wouldn't have life as we know it on the earth. Okay, so this is a miracle. The fact that water is polar is really a miracle. All right. So what's the big deal about the water molecules? Remember when we used the magnets last time? We stuck them together and how they stuck to each other. And if you looked at it closely, you would have seen that the red part sticking to the white part on the magnet. So also what happens is as a liquid, the molecules actually are pulled closer together. This is a little unusual. Okay, usually they would spread apart. Remember we talked about the phases of matter? And if they're the closest when they're a solid, and then they start to move apart when they're liquid, then they move apart some more when they're gas. But as a liquid, they actually pull closer together because of those hydrogen bonds. So therefore, it's less dense and floats as a solid. So when water is a solid, what is it called? It's called ice, which, by the way, we need some ice today. And so if you want to grab a beaker, we don't need very much ice. The ice maker should have ice. And yeah, that's great. Just maybe half full. That's all we need. If there's no ice in the ice maker, like if it's not working or whatever, I have a bag in the freezer. Okay. But we just need a half full there. Okay. All right. So why is this important? That it floats as a solid. Is that important for ice to float? Looks pretty in our cup, right? Yeah.
Well, it makes it on like the Antarctica.
Okay. It literally saves animals living in water.
I just like eating ice, like anything where you should like go like Chicken Express, you just eat their ice.
Well, especially if it's that kind of ice, kind of
like
softer and crunchy like that. I will tell you that cold ice crunching on your teeth is actually a little bad for your teeth because of the temperature and then the cracking could crack your teeth.
Does it make it sensitive to your teeth and then like hydrogen peroxide? Like I know my she'll like sometimes like people brush your teeth and it makes it sensitive. If you use it like every day.
If you use what every day, hydrogen peroxide? Oh yeah, I wouldn't use hydrogen peroxide every day.
If you swallow it.
Yeah, it's not going to be poisonous. Some people drink hydrogen peroxide, but a specialized
like
type.
Hydrogen peroxide and baking soda and sometimes like.
That'll really be fuzzy. Yeah, it'll be
Like they say, if you like mom said that she'll like do it maybe every few weeks or something like that. It just helps like.
Sure, it's very abrasive, and abrasive will scratch off plaque and stuff like that.
Every single day to make your teeth very sensitive.
Okay, all right. I didn't know that about it, that it would make your teeth more sensitive. I just knew that ice will make your teeth crack, which will make them sensitive. So no other substance is designed that way. If it weren't for this thing, then we would have lakes freezing from the bottom up, and the fish would die. All right. So the fact that it's less dense and therefore ice floats. You think about like an iceberg and things like this. They're floating. It keeps stuff from freezing, the water from freezing from beneath. All right, so we can see what happens here. So as a liquid, the water molecules are closely together, and when it freezes, look, they set up this on the right side, you can see they set up sort of a lattice work. So what happens is, because of those hydrogen bonds, it actually pushes it a little bit farther apart. Every other thing that we know, when you put it in the freezer, it contracts down and gets smaller. Water is different, okay? And you probably have seen this before. If you ever put your water bottle in the freezer to get it cold for the next day's picnic or something, and it can actually break the water bottle, right? It'll expand and it'll get bigger and the water bottle could break. If you put a glass bottle in, you might crack the glass. Mostly on those little like water bottles, the plastic water bottles, is if they crack, they're so thin nowadays, and the plastic is so thin, you can ruin it that way. But that's because of this. Those hydrogen bonds stretch out and they get very rigid as opposed to flowing, and therefore it moves farther apart. All right, so here we see, this is important for ice floating, right? I think we're going to get to a point where we talk about the difference between there's ocean ice and there's icebergs. Icebergs come from a glacier. They actually fall off of a glacier, and they're fresh water. But sea ice is actually frozen salt water. It takes a lot to freeze salt water because the salt makes it more difficult to freeze. All right, let's see a little bit.
I have a question.
Yes.
Can't polar bears, they can jump in there and be like fine?
Oh yeah,
Like,
they swim really, really well. There's nothing wrong with that polar bear.
How cold is it? Like if I was okay, I'll just jump in and get right back out. How cold would it be?
Oh, it's cold. Yeah, the
Like
water's cold.
below 0?
Because it's salt water. Well, so it's probably, I would say that it's around like 4 degrees or something like that. So too cold for us, yes, you know. So anything for us, like, what was the Titanic? I think the Titanic, it was something like 15 degrees, the water was. And that's why the people died, you know, because they were in that ice water. It was very, very cold, yeah. All right, we're going to watch a little video.
Life, as we know it, would not exist without water. Over 70% of the planet is covered in water, and our bodies are around 70% water. But why is water so important? The structure of a water molecule and the fact that it is capable of forming hydrogen bonds with multiple other water molecules simultaneously provides water molecules with some very unique characteristics. These include the ability to act as a universal solvent,
We knew that.
the properties of cohesion and adhesion,
We'll learn that today.
a high surface tension, a high heat capacity, and changes in density based on temperature. Let's take a look at each of these in turn. Water is often called the universal solvent, which means that many substances dissolve in it. Water's solvency has to do with the polarity and hydrogen bonding ability of water molecules. When a salt, such as sodium chloride, is placed in water, the negative ends of the water molecules are attracted to the positively charged sodium ions, and the positive ends of the water molecules are attracted to the negatively charged chloride ions. This attraction causes the sodium and chloride ions to break up or dissociate in water. Why is this important? Since our cells are mostly water, these solutions of ions and molecules allow chemical reactions to occur much more frequently, which is an important feature to allow organisms to respond to their environment. Water molecules are also cohesive and adhesive. The hydrogen bonds in water cause water molecules to stick together, a property known as cohesion. Polar bonds also give molecules an adhesive property, or the ability to cling to other polar surfaces. Why is this important? Well, water fills the internal transport systems of plants and animals. Because of these cohesive and adhesive properties, water allows for the efficient transport of nutrients and waste within an organism. Water also has a high level of surface tension. Because water molecules at the surface are more strongly attracted to each other than to the air above, water molecules cling tightly to each other. The surface tension of water explains why it beads up on waxy surfaces and why water-striding insects are able to walk on the surface of water. Water has a high capacity for heat. What this means is that the many hydrogen bonds that link water molecules let water absorb a large amount of heat without changing its chemical state, for example, from liquid to gas. This not only stabilizes the temperature of bodies of water, such as lakes and oceans, but also plays an important role in the physiology of an organism. Since life is based on water, and the temperature of water rises and falls slowly, living organisms are better able to maintain their normal internal temperatures and are protected from rapid temperature changes. And finally, the density of water is based on its temperature. However, unlike many other compounds which contract when they freeze, the configuration of the hydrogen bonds in water causes it to expand when it freezes. This expansion causes ice to have a lower density than liquid water, and therefore ice floats on liquid water. If ice were more dense than water, it would sink, and ponds and lakes would freeze solid, making life there impossible. Instead, bodies of water always freeze from the top down. The ice on the surface acts as an insulator to protect the water below from freezing. This protects aquatic organisms so that they can survive the winter.
All right, there we go. Okay, so here we're just showing it again where it's in a liquid form. On the left, you can see those molecules are slipping past each other. That's what makes a liquid, is when they're freely moving past each other. And then when they're a solid, they have those rigid bonds of the hydrogen bonds, causing that to have those stronger bonds. Hydrogen bonds are typically not super strong, like when we put salt in there, the salt will squeeze right in between. When they get solidified, they become much stronger that way, and they become very kind of stretched out like that. All right, so we can see our water right here. See our H2Os, and now they're going to start linking together. I think they're freezing at this point. Oh, now we're going to add salt. Oh, did I stop it when we added salt? When you add salt, it should go back to a liquid. So I don't know why the salt's coming in there. All right, sorry about that. I trashed that one. Okay, check this out. We have our fish that are just fine living below the surface. It's frozen on the top, but they're just fine underneath. Thank goodness for that. Otherwise, and you may think, well, what's the big deal? What if all the fish, froze every year? I don't like fish anyway. No, it would affect the complete ecosystem of the planet. Furthermore, it's more than just fish down there. We have like algae and things like that would freeze and cause the planet to be completely thrown off balance. Iceberg looks like this. I think, like I said earlier, that we will be covering icebergs later.
Pretty.
And you can see how the vast majority of this, an iceberg is freshwater, frozen freshwater, floating in salt water. So it floats well. But notice how the vast majority of the iceberg is under the water.
So the Titanic ran into
Yeah,
like
so it saw its little part sticking up like this, and the boat hit a bigger side. They knew that, of course. Everybody knew then even that the iceberg, the majority of it was underwater. So
they knew they were going to hit it.
they knew it. When they got close, they tried. It's hard to turn a big ship like that very quickly, and so they tried to move out of the way, and were not able to. In fact, by not hitting it head on, they probably caused the Titanic to sink. Yeah, so scraping along the side, it broke a lot of rivets on the side and caused it to take on way too much water. Okay, so cohesion right here, you can see, if you've ever noticed with a spider web, it catches the dew. I will tell you, it's also important for the spider's web to have that dew in there. It's designed by the spider to hold on to the dew, because it actually makes the web a lot more springy in there. Like it can move better and capture the prey more easily. So when we have really dry times, it's more difficult for the arachnids out there, because they're not able to use that cohesion factor right here. So with the cohesion, we know that they're sticking together, and they're sticking together really strongly right there, making that sort of, like this. So you can see it's a sphere. Okay, so if you can get water into a place that has no gravity pulling on it and keeping it down, for instance in space, that's what the water will look like, a complete sphere like that. And so the astronauts will do that. They'll put a little water in there, and they'll have to go suck it up with a straw immediately, because they don't want that big blob of water touching any of their electronic equipment, any of their computers, because as you know, we want to keep our computers free from anything that might short out the
That
circuits.
is fun to play with it and touch it.
Yeah, it kind of breaks up into little smaller pieces at that point. Yeah, so if you can break it, it turns into, and then they're going everywhere, so you have to be careful. And you can see right here, this is, if you can see it, if you could make it go slowly enough, you could see at one point when there's no gravity acting on this at that split second, you can see it's a complete sphere right there. So it's holding on to itself. All right, so that is how water, here it is, holding on to itself. So adhesion, though, is another thing. So cohesion is the way it sticks to itself through hydrogen bonding. Adhesion is how it sticks to the side of something. You've probably done with your straw in your lemonade or whatever, and you can get the lemonade to crawl up the straw and then take it out. And, this kind of, you hold on to it. Yes? Yeah. So it's called capillary action as it's pulling itself up a straw. A glass straw is even better. We'll pull it up even better because the water will stick to or adhere to the sides of the glass. This is exactly how trees, did we talk about that last time? How trees get the water going to the top? How we have that water being sent out through the leaves, which creates kind of a, I hate to use the word suction, but kind of like suction, but we have the cohesion pulling it up and replacing that which left out through the leaves. So the difference between cohesion and adhesion is what are they holding on to? If they're holding on to each other, that's cohesion. If they're holding on to the side, that's adhesion. So the tendency of water to stay together when it's exposed to tension. So surface tension. So at the surface, it actually increases the amount of strength or amount of that hydrogen bond holding on to it. All right, which brings us back to our water strider, right there on the water. And then I had this video in here about the water strider, but we watched it last week. Remember the British guy? So I'm going to move on from that. We're going to try this today. If you took general science with me, you've done this before. But we're going to try floating our paperclip on there and see if we can get that to do it. So what about hard water and soft water? Have y'all ever heard your folks talk about hard water and soft water? We have hard water. Have you ever had to clean your bathrooms? Do you have like crud on the walls of the bathroom over time? That's typically hard water mineral deposits. So Tricia, you may have softer water, which is nice. I remember the church we used to do the ODA at, the one in Bastrop First, they had a water softener, and the water softener used salt as the thing to help soften the water, which always messed up my science experiments because there was a little bit of that salt in the water, making the water less hard. The harder the water, the more surface tension you're going to have. We take the minerals out by putting some salt in, which kind of gloms onto and pulls them off. I thought I had a picture of that.
I'm pretty sure we have soft water because we have well water.
You think it's soft? Yeah.
But we don't know. Okay,
I'll give you a hint. Is it easy to lather up or is it difficult to lather? If you have a bar of soap, you make really good bubbles or not very good bubbles?
Good bubbles.
Good bubbles? Okay. So you can see here that soft water, hard water has a lot of minerals dissolved in it. So right here on the inside of this pipe of water, you can see the deposit of minerals, which over time can completely block the pipe. You can see it like on the shower head right here, or that's a drain, I guess, leaving those deposits there. My water is fairly hard, but not as hard as I had. When I used to live in Austin, we had really hard water that left, and we had black tile. It was very pretty black tile, but it would leave like a white kind of film on the black tile. After like 1 week, I clean it, and a week later, it's already got this film back on it. It was driving me crazy. Also, it would leave it on your glasses from the dishwasher. You would have spots and things in your glasses. So if you have really spotty glasses, you might have hard water. Soft water, all that's gone. That's why a lot of people like to soften the water, because it helps to maintain healthy pipes and things like that. So let's see if this person can give us some insight.
If you wash with soap using rainwater, washing is easy and there are plenty of bubbles. We say the water is soft. But if you use well or tap water, it's sometimes difficult to get a lather and the scum forms. In this case, we say the water is hard. Hardness is usually caused by the presence of calcium ions dissolved in the water. Water coming from rivers or wells has had to flow through the surrounding rocks, and if they contain soluble calcium salts, the water will become hard. So here's a question. Why do you think rainwater is always soft? Pause the video until you have thought of an answer.
It's like a filter.
Well, all the salts which dissolve out of the rocks end up in the seas. But when water evaporates, later forming the rain, the salts are left behind in the seas, meaning that the rainwater is always free of salts and therefore soft. However, gases from the air can dissolve in rainwater, and one of these is dissolved carbon dioxide. When rainwater falls on limestone, that's calcium carbonate, the limestone dissolves slowly, which is how the great caves full of stalactites are formed. Here's the equation.
Chemistry.
Calcium carbonate reacts with the carbon dioxide in the rain to form soluble calcium hydrogen carbonate. This form of hardness is called temporary hardness because boiling reverses the reaction and the hardness is removed. But the limestone will deposit in your pipes, on the cooking utensils, or in your kettle, forming something we call limescale. And this is also how stalactites are formed in those big caves. Another form of hardness is called permanent hardness, which comes from rocks containing gypsum, which is calcium sulfate. In this case, you do not get limescale, but you still, of course, get a scum with soap. So what is this scum? Well, soap is made by boiling natural fats and oils with sodium hydroxide. The soap molecules, for example sodium stearate, have a long tail which is attracted to oil or dirt, and the sodium ion end which is attracted to water. In this way, dirt is lifted off your hand and the clothes and is carried away by the water. However, calcium stearate is insoluble, so if the water contains calcium ions, the soap will not work until all the calcium ions have been precipitated out as scum. Detergents are sodium salts of compounds called alkyl benzene sulfonates, whose calcium salts are soluble, so there is no problem of scum with detergents. So to summarize, we saw that water becomes hard by flowing through rocks containing calcium salts, and these react with soap to form a scum of calcium stearate, making it difficult to use the soap. Temporary hard water forms deposits of limescale when heated, but rainwater is soft, lathers easily with soap since it's free of dissolved salts.
All right, there you go. So if your water is hard, it's more difficult to get your soap to lather up. I don't know about y'all, but I've had where I've used hard water, and then when you take a shower in soft water, you can tell the difference right away. It literally feels like it's slippery on your hands, and that's softer water. You know, where hard water makes you feel dry. You know, and your skin looks kind of dry afterwards. All right, so how do they soften water? Is they'll take some sort of thing like a resin right here, and this one looks like it's using, is that magnesium? Yeah, magnesium, or it's taking the magnesium out. So these calcium and magnesium will stick to the resin, and we get that out of there, and you end up with the minerals gone. I know another way to do it is using salt, and you may have seen giant bags of salt, rock salt, that people will put into their water softener. That's very common around here. So it must work really well with the limestone water that we have, because we have a lot of limestone around here. All right, so recap the properties of water. Its composition is 2 hydrogens to 1 oxygen, that's H2O. It's a polar covalent substance. It's the universal solvent. It is less dense as a solid than a liquid, therefore it floats. It has surface tension, and it's attracted to other surfaces. So if y'all wanted to get your phones out and take a picture of the slide, this is some good summarization. Say again?
Stuff to study for next week.
Right, for our quiz next week. It might be a good one. And to know what each of these things means. Today we'll be looking at surface tension, so it should, hopefully the idea of the lab is to help you understand and apply whatever we've learned here, okay? So now it's already time for lab. How about that? We might get out early today. So we're going to do several lab things working with water, okay? So Anne-Marie, if you could get everybody a bowl of water. There's water in those beakers over there. And then give everybody a few paper clips. We can start with our paper clips, trying to float those. All right, and so I'll just put this up there for those who are missing. These are our labs we'll be doing today. And next week, be ready for the quiz.
Yeah, allergies kept hitting me hard because I like stopped doing hydro the other night. I was like, I can't breathe.
All right.